Hey there, Math 1. Today we are starting Chapter 7, Section 4. This starts us on a topic that some people really enjoy and some people do not. And that is writing a geometric proof. So today we're going to do the beginning of learning how to write a proof. Let's get started. So, you can see here that definitions and properties and theorems. What are those? When we start trying to prove things in geometry, that is, we try to make an argument. I really like proofs because it's really just trying to argue that something must be true. It's trying to argue your point. We will need to blank our statements. So when you're having an argument, you just can't make a statement unless you have something to back it up with, some type of proof. And we call that justify. We need to be able to justify our statements, or that is, give a reason why our statement is true. And the way you do this in geometry is with definitions and properties and theorems. And we're going to look at some of those today. So a good definition, maybe a property or a theorem, is really an if-then statement. I'm not sure you know what an if-then statement is. An if-then statement basically says if something is true, then something else must be true. And I have an example here that we're all familiar with, and that is the definition of a right angle. And over here, I have given us the definition of a right angle. It's an angle that has a measure of 90 degrees. But as a right angle has a good definition, you can write it as an if-then statement if you chose to. And it would look something like this. If an angle is a right angle, then it must have a measure of 90 degrees. Right? So that would be the definition of a right angle written as an if-then statement. Now you might say, why am I writing the definition as an if-then statement? But there's a method to my madness here, so stay with me. All right, so if-then statements, which you will learn later in math, if-then statements have what is called a converse. And a converse is when you switch the if and the then. And for a good definition, the converse of it is true as well. And let's go over the right angle definition with that. So the converse of the definition of a right angle would be if an angle has a measure of 90 degrees, then, it must be a right angle. See how that works both ways. If it's a right angle, then it's 90 degrees, or you can switch them. If it's 90 degrees, then it's a right angle. That does not work for all statements. Let me think of one that it does not work for. For instance, if today is Saturday, then it is the weekend. Now that would not be true if I switched it, would it? If I switched that, called the converse, and I said, if it is the weekend, then today must be Saturday. Well, that would not necessarily be true because today might be Sunday, right? switching the if and the then, not always true. But it is for a good definition. All right, so what I've given you here is a reference list of many definitions, properties, and theorems. And we are going to look through this very quickly, but this is a reference sheet that you should keep handy to help you do proofs. All right, so I have this first definition, which you're probably not familiar with, would be my guess. The definition of congruent. Do we know the symbol for congruent? Right? The symbol for congruent is an equal sign with a little wavy line over it. And it says, okay, and I've written all of these as if-then statements because I think they're more understandable to use in a proof this way. So it says, if two figures are congruent, then they have equal measures. That is the definition of congruent. I would like to point out that like figures are congruent. A figure would be like an angle or a shape. Like I might say that angle 1 is congruent to angle 2. Measures are equal. I might say the measure of angle 1 equals the measure of angle 2. I would never say that angle 1 equals angle 2. When I'm talking about figures, I use the word congruent. Congruent means they have equal measures. Measures are equal. Figures are congruent. All right. Complementary angles, we know what those are. They are, if two angles are complementary, then their measures have a sum of 90. Supplementary angles, we know what those are. A right angle, we certainly know what those are. So those are all definitions, right? These first ones, maybe I should have made a note of that. So these first ones are all just definitions. And when we use them in a proof, we will say because of the definition of something. But then we get to some theorems. Theorems are like rules in geometry that we can assume they're true. Theorems are actually things that we can prove to be true, and we might do that at some point. But right now, they are just rules that you can assume are true. And the first one we have is the vertical angles theorem. We know the vertical angles theorem. It says if two angles are vertical angles, then they're congruent. Notice it says the word congruent. It does not say they have equal measures. It says they're congruent. All right, we'll get back to why that's important in a little bit. Then I have the linear pair theorem, which says if two angles make a linear pair, then they are supplementary. Notice it says supplementary. It does not say add up to 180, though they would add up to 180 because they're supplementary. Then I have the alternate interior angles theorem, right? That's when you have parallel lines and you have these two angles. If two angles are alternate interior angles between parallel lines, right, that's a whole bunch of stuff in the if. But if you have two angles and they're alternate interior angles and they're between parallel lines, then they are congruent. That is what the alternate interior angles theorem says. And the corresponding angles theorem, right, it says something very similar. It says that two angles are corresponding angles between parallel lines, then they are congruent. And same side interior, it says something similar. If you have two same side interior angles and they're between parallel lines, then they are supplementary. And we come back, J, same side exterior angles, very similar. If you have two of these, then they're supplementary. And that takes care of our theorems for the moment. All right, by the way, all of these definitions and all of these theorems that I'm giving you, we could actually double them because we could say, and their converse. All right, so I could say if two angles have measures that have a sum of 90, then they are complementary, right? The converse works for all of these as well. So there's actually double the amount here. All right, where was I? Let's finish up. We're going quick here. All right, starting with the transitive property then. These are a bunch of algebra properties. They're just a bunch of algebra properties. The transitive property says if A equals B and B equals C, then A equals C. You know, I like to point out that, of course, this is true because A is equal to B and C is equal to B. So if A and C are equal to the same thing, then they must be equal to each other, right? The substitution property is one that you should know well because we just got done solving systems of equations by substitution. It says if two amounts are equal, then one can replace the other in an equation. For instance, if you have y plus 3 equals x, and you have 2x plus 4y equals 50, then you can take this because it's two amounts that are equal. Well, these two amounts are equal, so I can replace the x with what it's equal to. And that is just the substitution method, the substitution property. All right, the reflexive property. This is a weird one. It's kind of stupid, but you'd be surprised it gets used all the time. And it just says that an angle or a side is equal to itself. You know, a lot of people remember this as reflective. Like I'm looking in a mirror, reflection, I just see myself. This just says something like x is equal to x, or angle 1 is equal to angle 1. All right, that's all set. Something is equal to itself due to the reflexive property. All right, then come these ones you use in algebra all the time. These are 4 different properties, but they all basically are the same. They say if you have an equation that is equal, two amounts that are equal, like A equals B, and you do the same operation on both sides, then they're still equal. For instance, if I had something like x plus 3 equals 10, right? I would subtract 3 from both of those and get x equals 7. I have just used the subtraction property of equality. All right? I took two amounts that were equal and I subtracted the same amount from both of them. And it's still equal. The two amounts are still equal. That is the subtraction property of equality. If I added something to both sides, it would be the addition property of equality, right? If I divided both sides by something, it would be the division property of equality. All right, and last up is the corresponding parts of congruent triangles are congruent, better known as CPCTC. We will see that not for a week or so, at least probably. All right, we're going to do some examples and we'll be done here. All right, so there's 2 ways that we will look at to write a geometric proof. We have 2-column proofs and we have flowchart proofs. And today we're just going to look at the 2-column proofs. Remember, a proof is just an argument. Why something is true, you're just making an argument. All right, but you have to have reasons why your argument is true. Now, the first step or statement in every proof is the given information. Right? That's always going to be your first step, or 99% of the time, that's going to be your first step. Then, based on that, you can prove other things must be true as well. We put statements on the left and reasons why they are true on the right, called justifications. And then the last step in every proof is the blank, 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 blank to blank. Any idea what that is? It is. The last statement is the thing you are trying to prove. Yeah, it is. So here we go. I'm starting out with two-step proofs. These are exceptionally easy, right? These are just the given and the conclusion, or the thing you're trying to prove. So it's given that the measure of angle 1 plus the measure of angle 5 equals 90. Prove that angle 1 and angle 5 are complementary. So if I was doing that in proof form, it would look like this. First, my first statement is going to be the given information. The measure of angle 1, that's a horrible angle, isn't it? Plus the measure of angle 5 equals 90. How do I know that's true? It was given. And now I'm ready to say what I'm trying to prove. Angle 1 and angle 5 are complementary. How do I know? Well, I know because of the definition of complementary, which is if two angles add up to 90 degrees, and I have said they add up to 90 degrees already, then they are complementary. And so all I write here is the definition, and you can always abbreviate definition with DEF, definition of complementary. That's how you know they're complementary, because they add up to 90, and that's the definition of complementary. Next one. These short ones are almost confusing because they're too easy. All right, it's given that the measure of angle, or it's given that angle 1 is congruent to angle 7. Let's write that in. Angle 1 is congruent to angle 7. And I know that's true because it was given. All right, I want to prove that their measures are equal. Okay, well, now that I've said they're congruent, do I have enough information to say their measures are equal? I do. I can now say the measure of angle 1 equals the measure of angle 7. Again, this is a definition, because once I've said they're congruent, I can say by the definition of congruent, I like to use the congruent symbol, by the way. The definition of congruent says that because they're congruent, therefore their measures are equal. So because of step 1, therefore step 2 must be true. If two angles are congruent, then their measures are equal. All right, example 3. Wait a minute, I think I missed one. No, I didn't. Did I miss one on the last page? No, don't know what I'm doing here. All right, next one. Given that, let's see, angle 8 and angle 9 are vertical angles, prove they are congruent. All right, so first I'd write my given information. Angle 8 and angle 9 are vertical angles. That is given. All right, well, this is a two-step proof, so obviously I can now give what I'm trying to prove. How do I know that the angle 8 is congruent to angle 9? Well, it's right back here, right? It's not there. It's not there. It's still not there or there. Where did it go? I've lost it. Did I miss it, you guys? No. Oh my goodness. Huh. Well, that's interesting. I feel like, oh, there it is. The vertical angles theorem. It says if two angles are vertical angles, then they are congruent. Sorry about that. So now that I've said they're vertical angles, I can use the vertical angle theorem. And I can say that because they're vertical angles, therefore they're congruent. All right, last two-step proof. given that the measure of angle 2 equals the measure of angle 5, and the measure of angle 5 equals the measure of angle 9. Oh my. The measure of angle 2 equals the measure of angle 5. And this fit better on paper than it does for me on the board. The measure of angle 5 equals the measure of angle 9. That was given. Can I prove that the measure of angle 2 equals the measure of angle 9? I can, because look, they are both equal to 5. What property says that if they both equal the same thing, then they equal each other? Well, that would be because of the transitive property. Now, I got to show you something. When I am doing things that are equal, like this, measure of angle 2 equals measure of angle 5, comma, measure of angle 5 equals measure of angle 9, given, there's actually another way to do it. Do you see it? The other way to do this one would be to say, all right, because these are equal, I can take this guy and I can substitute him in for this guy over here. And so I'm going to rewrite this sentence, but I'm going to make the substitution. And that would be the sentence if I make the substitution, wouldn't it? This could actually be done by substitution. And I use substitution a lot more often than I use the transitive property. All right, I've got two more. I know this is a relatively long one because I had to go over that reference sheet. I'll be done in a minute. All right, a three-step proof. So let's write the given in. The measure of angle 1 plus the measure of angle 4 equals the measure of angle 2 plus the measure of angle 4, and that is given. Can I prove that these two angles are congruent based on the given? Anybody see how to do it? Well, if I want to prove that these two angles are congruent, and this is very often how I do a proof, I work backwards. If I want to prove that these two angles are congruent, I need to prove they have equal measures. How can I prove they have equal measures? I think I see it. I think I can say that the measure of angle 1 equals the measure of angle 2. And all I did was get rid of this guy. Essentially, I did algebra. I subtracted the measure of angle 4 from both sides. This would be the subtraction property of equality, which you can abbreviate the SPO. The SPO means this. It means I subtracted the same thing from both sides and they're still equal. That gets done in algebra a lot. And now that I've said that their measures are equal, now I can say they're congruent. Because they're equal, they are congruent. That is the definition of congruent that says that. It says if their measures are equal, then they are congruent. All right, I got one more, the big fella. Four-step proof. Here we go. Let's write down the given. K is parallel to N. All right, I want to prove that angle 4 is congruent to angle 8. Now, I do know it's true because the corresponding angles theorem says it. But what I'm actually trying to prove here is the corresponding angles theorem. I told you we could prove a theorem is true. And this is one we're going to prove. We're going to prove that this is true without using the corresponding angles theorem. You can't use the corresponding angles theorem to prove itself. That's not legal. So, how am I going to do it? Well, I'm looking, I know that angle 8 is equal to angle 6, right? And you know what? I know that angle 4 is equal to angle 6. I think I've got it. I think, let's see, how about this? How about angle 4 is congruent to angle 6? Do you guys know why that's true? It's true because, and this is actually how I write it out, I would say something like alternate interior angles between parallel lines are congruent. AIA, alternate interior angles, that's a BTW for between. I'm not going to write out the whole word between. Alternate interior angles between parallel lines are congruent. You know, this is the alternate interior angles theorem. But I actually like to write it out because it tells you what the theorem says. And I can also say in my next step, so now I've proven that 4 is equal to 6. And now I can say angle 8 is congruent to angle 6. That one is because of the vertical angles theorem. All right. And now I've got it. So now, because 4 is equal to 6, I'm allowed to take 4 and substitute it. So I can say angle 8 is congruent to angle 4. All I did was substitute. That's by substitution. I took two amounts that are equal to each other, and I substituted one in for the other. And I have proven what I was trying to prove. All right, 27 minutes. I know it was a long one. I'm sorry. You're going to have a great day off on Monday. If you are the blue, well, everybody's going to have a great day off on Monday, right? I will see you guys next time.